So, good morning to each and everyone present here. So today we are having the lecture in the series of the lecture. We are having the lecture of Dr. Chandrasekhar Prasad on leaky wave beam steering antenna. So before starting the lecture, I want to introduce Dr. Prasad to all the participants. So Dr. Prasad received his BTech in Electronics and Communication Engineering from Kalyani Government Engineering College, West Bengal, Kolkata. He received his MTech in RF and Microwave Engineering from Jadavpur University, Kolkata, and PhD in RF and Microwave at in the Department of Electrical Engineering from IIT Kanpur. He is currently working as an assistant professor in the Department of Electronics and Communication Engineering, NIT Hamirpur. Before joining here, he was involved with the NIT Delhi, and he was handling as an assistant professor there in the Electronics and Communication Engineering. He has authored and co-authored more than 25 journals, reputed journals, and the conferences. He is the active member of the IEEE Antenna and Propagation Society and Microwave Theory and Techniques Society, IEEE. His research interest includes dielectric waveguide, dielectric image line based antenna and circuits, leaky wave, and the wideband high gain antennas. Not limited to these, there are many more. So, handing over to Dr. Prasad.
Thank you, Dr. Saurabh. Am I audible?
Yeah.
Okay. So good morning, everyone, and let me share this slide. Okay. So is it visible?
Yeah, it is visible.
Okay. Okay. So let me start. So in this lecture, I am going to talk on leaky wave antenna. Basically, using that, we can rotate the beams and scan areas. So in this lecture, I will talk briefly about this. What is leaky wave antenna and why it is important. Then I will try to talk on this physics of leaky wave antenna. Then I will talk about the design challenges and we'll see some examples. Then I will conclude my lecture. Because we have a limited time of 1 hour, so I will try to finish my talk within 50 minutes, and next 10 minutes I will put for this question answer, if you have any. Okay, so before going to this leaky wave antenna, first see we can broadly divide this antenna into categories based on this their wave containing properties. Like one, we can say this resonating structure, and one is non-resonating structures. So many antennas like dipole antenna, patch antenna, dielectric resonant antennas are in the category of resonating structure. Similarly, we have non-resonating structures also, like we have dielectric rod antenna, helical antenna, horn antenna, etc. So just see what is this advantages and you can say limitation or disadvantages of these two categories. So you all know about this resonating structure. So since we have resonance, so generally resonance occurs as a single frequency theoretically. So we have narrow impedance bandwidth. And if you see this patch antenna or dipole antenna, so radiation is basically in one fixed direction. And directivity is comparatively low. So to have this high directivity, we have to go for this antenna arrays. Advantage is we can have a small size that is maybe limited to lambda by 4 or lambda by 2 and so. So these are some basic advantage and disadvantage. And if you come to this non-resonating structures, so we have, since there is no resonance, so basically wave is traveling, so we have wide impedance bandwidth. And one other advantage is this radiation or beam direction may be in different direction at different frequency. And since we have high length is large, so we have high directivity, and we have simple feeding structures. And disadvantage is this large size. Fine. So with this, I will come to this non-resonating part, that is traveling wave. We say this part, non-resonating part, as traveling wave structure. So here again, we can divide this in two parts, traveling wave antennas. One is called surface wave antenna and one is called leaky wave antenna. So basically in surface wave antenna, this wave propagates over the structures and radiate at the end. So we have like end fire radiation, or you can have, if you put some ground plane, so you can have off broadside radiation. Now, if you perturb this traveling wave structure, then we can have this radiation that is called basically your leaky wave antenna. So to have this leaky wave, basically we perturb the structure, not rigorous, but in a small amount, so that we can have a small amounts of leakage and we can have radiation. So to have this leaky wave, we have to first do the periodic perturbation and permit some higher order modes to leak out. So this is the fundamental things to design periodic leaky wave antenna. Now, if you come to this application of leaky wave antenna, so we have many applications like radar system, and similarly we can have wireless communication system like 5G. So this is basically used for beam forming, because we can rotate the beam by changing the frequency, beam steering, and multiple input, multiple output, that is called MIMO system. Similarly, we can have this application of leaky wave antenna in satellite communication. So we have broadband impedance, so we can have broadband communication, broadcasting, and internet access services. And here we can have the use of this leaky wave antenna in medical imaging. Similarly, we can have this imaging at maybe airport, seaports, industrial inspection, and so. Similarly, we can have the application of this leaky wave antenna in direction finding. So with this, now come to the basic principles of leaky wave antenna. So before going to the basic principle of leaky wave antenna, first see this wave equation. Fine. So you might be you know this. If you solve this Maxwell's equations in phasor form, so you'll get this equation. This is, and now if you solve this, so here we put this gamma. Gamma is basically your alpha plus j beta. You might have this study in your UG courses. So this alpha represents your attenuation, and this beta is basically phase constant. So these two parameters are important to do the analysis of leaky wave antenna. That's why I have given here for your recap. Now, if you solve this wave equation, so mathematically we have this solution. Some E naught e to the power minus gamma z and E naught dash e to the power plus gamma z. So this first part represents a wave that is propagating in positive z direction, and this second part is representing a wave traveling in negative z direction. Similarly, this, if you put the value of gamma, so this will be converted like this, E naught e to the power minus alpha z e to the power minus beta z. Now here, important catch is here. This e to the power alpha, e to the power minus alpha z basically represents your loss. So if you have some guiding structure or any structure, so alpha basically represents the loss. So this loss may count, maybe dielectric loss, conductor loss, and radiation loss if you have any radiation. So that's why this alpha is important for leaky wave, because we'll do the analysis in terms of loss from the structure, and that will be your radiated power or radiation. Now see the second part, that is propagation factor. So now if you see just if beta is 0, so this part will vanish. And then this equation, you can say, will not represent a propagating wave anymore. So that means to have a traveling wave, this beta must be real, right? So I have written here, if beta is 0, so no propagation, and that will represent a standing wave. Now, if this beta is imaginary, so this part is imaginary, and here we have J. So basically, this will represent again some attenuation. So only attenuation, no propagation. So catch here is, for propagation, beta must be real so that we can have a propagating wave. So we can write this in some other forms, the same combination. So we can write this in E naught e to the power minus j kz z, where kz is, we have combined alpha and j beta in kz. So this is beta minus j alpha. This is basically a propagation constant in some other forms. So just remember this thing. This is important for our leaky wave antenna design. Now, if you see the general solution of wave equation, so this previous discussion was for only if wave is traveling in one dimension, that is, let's say, in z direction. Now, if you write this in general form, so let's say your wave is propagating in some r direction, and this is wave number k. So this k will have three components in x direction, y direction, and z direction. Similarly, we can write this r. So the general form is E naught e to the power minus j kxx, and so. So from here we write this k equal to kx square plus ky square plus kz square. And now if this wave is traveling in Fourier space, so we can put this k as k naught, and then this equation must be valid. Means to have this wave propagation, this relation must hold. This is also important. Now coming to the generic representation of a leaky wave radiation. So here this structure is like some wave is traveling here, and we want some radiation in this direction, means out of the structure. So I urge audience to please see this carefully, because this is the most fundamental things for leaky wave antenna understanding. So wave is traveling in, let's say, z direction, and wave, we want some power to come out from the structure in some this r direction. So we can put this in a cylindrical coordinate system, or maybe in XYZ coordinate system, rectangular. So this structure is lying in z direction, z axis, and we want radiation, you can say, in XY plane, fine, out of this structure. So this coordinate is represented by rho. So this is the general expression, you can say, for general wave equation expression. So from here we can write this k naught. So this will be kxx plus kyy kzz. Now this part is in it's perpendicular to, you can say, the structure, perpendicular to the z axis. So we can put this as k rho rho, and this is kzz. So we can write the same equation using this form. So we can replace these guys in this E naught rho e to the power minus alpha z, or e to the power minus j k rho rho, and then beta z. Basically, we are replacing this kz in terms of alpha and beta. Fine. So here now k naught square is just this was k naught square was kx square plus ky square plus kz square. So we are replacing this. Now this k rho, from this equation we can write this k naught square minus kz square. Now just recall this to have some wave coming in this rho direction, or perpendicular to, or you can say out of this structure, this k rho must be positive, or you can say real. So to be real, this should be real. So when this will be real, when we have this relation. And here we are putting k value of kz, that is beta minus j alpha square. So here if you we are assuming that the alpha is very small compared to beta. That means your loss is very small compared to this beta. So to have this k rho real, this relation must be there. So what is the meaning of this? So if you put the value of beta and k naught, so this is basically in terms of phase velocity. So the phase velocity Vp by c must be greater than 1. And this is called basically fast wave. Right? So this part is important. That means to have some leakage or power outside of this structure, you need some fast wave propagating in this, or to generate some fast wave so that your some power will come outside. So this is one catch to design this leaky wave antenna. So to have this leaky wave antenna, you must have some fast wave. Here I am talking about general structures. So there are some artificial designs like metamaterial and so. So there we don't need this condition. Fine. So, but for general structures, you have to have this fast wave. Fine. For that, this condition must be there. Now, if you see this structure, so you can find the direction of radiation, this theta naught angle here. So from this diagram, you can say, you can find this theta naught, that is will be sine inverse beta by k naught. So this will decide the direction of radiation. That means your beta is important to decide this region, that is fast wave or not, and also the angle of radiation from the structure. Now see the field behavior of leaky waves. So here, let's say we have two-dimensional things. That means let's say here this is x and z plane, and this y-axis is perpendicular to this. So we can write leaky wave that is propagating in z direction, and this electric field is oriented in y direction. So in this form, and where kz is, we can write like this complex wave number beta minus alpha. Fine. So the field behavior in the air region above the aperture means this is aperture, and the field behavior over this in, you can say, in x direction. So we can write x component and this z component and x component. So vertical wave number, that is the wave number in x direction. We can write this k naught square minus kz square, because k naught square must be equal to kx square plus kz square. There is no variation in y direction, so hence this ky is 0. Fine. Similarly, we can denote this kx in terms of this beta x minus j alpha x. Now, if you equate the imaginary parts, so we can have on this. Fine. Just put this here and this here and equate this imaginary part. So we'll have beta alpha equal to minus beta x alpha x. This relation. So from here, this, let's say this part beta is positive, that is this beta is for beta z direction, and alpha is negative. That means when this is traveling in positive z direction, and this we are assuming that this alpha is negative. So that means here we have negative sign, right? So energy will be leaked in positive x direction, right? So the representation of this, you can see from here, some wave is traveling in this direction, fine, and some leakage is going outside, fine. So if this alpha x is negative, that is in x directed wave is increasing exponentially, right? So wave is traveling in this direction and radiation in you can say outside the structure or in x direction is increasing. So this seems like improper or non-spectral, because wave is traveling and your energy outside is increasing, right? So this is called improper or non-spectral wave. So basically, physically, that is not happening. The power is coming outside, and the power going in, you can say, z direction, or in this structure is that is decreasing because of leakage. So if you see these two powers in combined form, so basically that is, you can say, constant. And if your alpha x is positive here, then this is called proper wave, and you will have this type of uh, power flow graph. Fine. So this is about just what is the proper wave and what is improper wave. Now coming to leaky wave part. So as we discussed, hello, am I audible?
You are audible.
Okay. So if you come to this leaky wave part, so as we discussed, to have this leaky wave, we need fast wave. So now question is how to generate this fast wave. So if you see the common guiding structures, that one is that is hollow metal waveguide. So this is by nature, this is fast wave. So we can have easily this leaky wave radiation from this hollow waveguide if you have or put some opening at suitable place. So we can have easily this leaky wave or leakage from this structure. Then other common guiding structures are like substrate integrated waveguide, that is very famous, that is SIW. You can say the planar form of metal waveguide. Then we have coaxial cable, then microstrip line and CPW. Then we have dielectric waveguide. So all these waveguides are generally slow wave structures. So how to generate the fast wave? So for that, we do the perturbation or periodic perturbation of in the structure. So we will do some periodic function of periodic perturbation in the structure. So now you know this theory. If you have periodic function of time, then we apply Fourier series, fine, and then we have infinite number of frequency harmonics. Similarly, if you have periodicity in a space or a periodic function of a space, so we have Floquet wave expansion theory, and that gives you infinite number of space harmonics. So basically, we are doing the periodic perturbation in a structure that is related to a space. So that means after doing that, we are going to have infinite number of space harmonics. So here we'll term this as space harmonic, not frequency harmonics. So this part is also important for your leaky wave antenna design. Now coming to this periodic structure. So here I have shown some microstrip line, and then there is some perturbation of this microstrip line. These are basically stops, fine, and these red lines denotes one period of perturbation, fine. So if you apply this Floquet wave expansion, so we can write this electric field or maybe magnetic field in this format. Here, this KZN represents, you can say, this nth space harmonic, and this will be like KZ naught plus 2 pi n by p, where p is the this length period, you can say space period, and this n is n represents the number of harmonics, means which number of harmonics. Like let's say if you put k j1, so first harmonic. If you put 0, so that means fundamental harmonic, and so. So this is representing nth Floquet mode, and this is a space harmonic, right? This part kz naught is, we can write this beta naught minus j alpha, fine. So again, this alpha is representing this loss, and beta is your phase constant. Important part or to remember is this beta nut is basically when we don't have any this perturbation. So beta is basically phase constant of this unperturbed transmission line, right? So we can calculate this. Now, so when we are loading this periodic part, then we can have this nth harmonic. Fine. Now, out of this n number of harmonics, some harmonics may be fast. Fine. And that harmonic is going to participate in your leakage. Fine. So we can put here this beta n minus j alpha n and then this right hand side. And from here you can write this beta n is beta nut and plus 2 pi n by p. So now this equation is very, you can say, fundamental for leaky wave antenna design, because we have to find this and decide which harmonic is your fast wave harmonic. Fine. This alpha n is always equal to alpha, means all space harmonics have same amount of leakage. Fine. Now, so this equation, and this equation. And now we have this angle of radiation as we have discussed this. We have one more term that is related to this leaky wave, that is called Bloch impedance. Fine. And we'll find this, I'll discuss this again using this equation. Fine. So this is basically in terms of ABCD parameters. And once we have this relation in ABCD parameters, so we can write this in terms of a scattering parameter or S parameter. Now we have this, you can say, phase constant of nth space harmonic, this relation. So we can do some mathematical manipulation and we can have this equation. Now, if you plot this equation, fine. So we'll have this type of graphs, fine. And if you change the value of n, so this graph will just shift, because if you see this is a linear equation like y equal to mx plus c. Fine. So if you change this part is constant for a given n. Fine. So if you change this n, your you can say this constant will change c. So this graph will only shift. Fine. So here we divide this diagram. This is called Brillouin's diagram. Fine. This is also important to see this dispersive characteristics of your design. So if you see in this region, if you have your graph or your value in this region, so this region is basically fast wave. So you'll have this region only if this beta n by this beta nut is I think less than 1, that will give you a fast wave region. Fine. So this will represent fast wave region. Fine. And within this fast wave region, this part, you can say, if you take this coordinate system, so this is, you can say, radiation in this direction is called backward region, and radiation in this region is called forward region. Right. So this is simply plot of, like this plot is like your omega beta plot. For we have plotted this for many structures like waveguide, etc. So this is like your omega beta diagram. Here there are some triangles here. These are called, if you have your data in this region, so that means your wave is bounded to the structure. So you will not get this radiation. Fine. So this is only radiating area. So we have to design so that our this dispersion diagram is we have data in this region. Fine. Then we'll have this leaky wave. Related to this leaky wave, we have some other terms. That is, one is called closed stop band and one is open stop band. First, let me discuss this closed stop band. Closed stop band is the like your wave is not propagating in the structure in terms of like if you are operating a waveguide below cutoff, so then the behavior of the wave is called closed enclosed stop band. Fine. This term is new for this leaky wave part, open stop band. So here just see this structure again. So when we are launching wave on this structure, fine. So some part will radiate out, fine. Some part will go down the structure, and some part will be reflected back, because here we have different you can say geometry. Then we have simple line, then again perturbation, then again line, and then so impedance is changing. So we all these things will happen. So there is some you can say reflection from each perturbation. Fine. And now if you have this relation such that all these reflected waves are adding to each other, then we'll have situation that this will block, this reflected will block the incoming wave. Fine. And this will basically stop the incoming wave, and there will be a standing wave in the structure. And at that point, we may have some radiation, but your radiation will degrade drastically. Fine. So that is basically not desired. Fine. And when it will happen, so you can do this mathematical this. So it will happen when we have this beta naught p equal to 2 pi. Fine. So if you see this value beta naught p equal to 2 pi, so for this, if you calculate this angle of radiation, so this is 0 degree. That is at broadside. So this when we have this open stop band, then that means there is a degrade, means your radiation will degrade at broadside. That means in general you can say will not have good radiation or radiation at broadside. Fine. So that means when we are designing leaky wave antenna and we want radiation at broadside side, so we have to mitigate this. So this is one biggest challenge to design this leaky wave antenna, and that is written here in text. So far I discussed the physics, or you can say basic principle to how to get this radiation from leaky wave. So and different condition for that. Now, so we have this equation and this equation. Fine. So these are in terms of beta. So how to get this in simulations? Fine. Or in measurement. Fine. So you can find this in terms of a scattering parameter. Right. So this beta NP is given by this equation, and I have taken this from this DM Poser books, and you can find this from any book or text which deals with periodic structures. So this relation is there, and then alpha P is this one. So this same thing, only this is imaginary part of this and this is the real part of this. So let's say this is your structure that is going to leak energy. So now question is what should be the length of this structure? So that is decided by how much radiation is basically needed, or when we can say that this antenna is radiating properly or a structure is radiating properly. So general cutoff is if radiation efficiency is 90%, then that length is okay to design leaky wave antenna. Meaning of this is like, let's say if you are putting 1 watt of power, right? And here at the second port, we are getting, let's say 0.1 watt of power. So that means 0.9 watt, or you can say 90% of the power has been radiated or lost. Because if you have some structure, so there will be some loss also. So this is general, you can say design guideline to have 90% radiation efficiency. And this is given by this equation. So you can put here 0.9 and you can calculate the value of this L. So this value of L will depend on this alpha, right? Because this is representing the loss. So here we'll not means we'll use the term not attenuation constant, but will leakage constant, right? So these two alpha L. So if your alpha is relatively high, so your this L length of the structure will be relatively low, and so on. So we can do some trade-off depending on your our requirement, fabrication, this limitations, space limitation, and so fine. Similarly, we can use this relation to calculate half power beam width. Fine. So now coming to the main challenge of this leaky wave antenna design. So the main challenge is this open stop band. Fine. So that is we have to mitigate this open stop band phenomena to have radiation in broadside direction. Fine. So how to mitigate this? Fine. So just see why we have this problem, because we have this let's say perturbation or periodic loading, and your wave is we have launched the wave. So here we have simple transmission line, then suddenly we have this disturbance, and then again we have simple transmission line, then again this disturbance. So this is coming in picture, this open stop band phenomena because of this reflection from this perturbation or periodic load. So now idea is, let's say when you are calculating, let's say input impedance here or input impedance of the line, let's say this is Z naught characteristic impedance. And if you calculate this input impedance here, let's say that is Z, and if these two are same, then we have impedance matching. So this reflection will vanish. Fine, this reflection will vanish. So that means this will vanish. So we can mitigate this open stop band phenomena. So now this Z is important, input impedance, and this was here, I just discussed, this was your blowage impedance. So that means we have to calculate this using this relation. This relation is in terms of ABCD parameter. So we can convert this in a scattering parameter, and we can find this. So in summary, we can say that this mitigation of open stop band is this matching of this unit cell. We say this one part is unit cell impedance with this main transmission line characteristic impedance. That is the important part. So with this, come to some design examples. So I'll discuss some design based on this slow wave structure. So let's say how to tackle this problem. And so let's say we have microstrip line or SIW or dielectric image line or waveguide. So these are basically slow wave structures. So what to do? So again, idea is same. Just do some periodic loading to generate fast wave because we need fast wave. So we'll have this open stop band at broadside, and that is challenge. So to mitigate this open stop band, we have to use some techniques to do the impedance matching. Fine. And that is the main, you can say, design challenge. And if you see research papers, so most of their means challenge is same. Fine. And the solution may be different way of solving the same problem. So here, let's say this is based on dielectric waveguide. So we have a dielectric waveguide. So we can do this perturbation in two ways. We can put some metal strips, or we can put some this that is called grating. Means we are putting some blocks of different material, dielectric material. So this is also some periodic structure. So these are the general two way to perturb this. So here one example is, so this part is your Leaky wave antenna. So this is dielectric image line, and here perturbation is metal. This is metal strip. So this is H-shaped. Fine. This is published paper in MOTL. So why this is H-shaped? So I'll show why. So let's just see. We are putting simple perturbation, means we are putting some metal strip. Fine. So in simulation, so what we do? We calculate input impedance. What will be here input impedance? Fine. So now if you calculate at this plane input impedance, and if this impedance is equal to the impedance of unperturbed line, then there will be no reflection. Fine. So your line will be matched with this unit cell, you can say, or this perturbed part. So we'll have proper propagation, and your open stop band will be mitigated. So that is the purpose. So if you have only this strip, so just see this what will be the real part of input impedance, and this input impedance is calculated with this relation. If you have S parameter, so we can get the S parameter just putting ports both sides and just simulate this structure. So you will have this. And if you plot for different widths, so this is the width. This green line is this J port. That means this is the impedance or characteristic impedance of this line, unperturbed line. So that means we want the real part of this section close or equal to this green line. Fine. So there is the plot is for different widths. So if you see, so this black line is closest to this, and it is following the same pattern with frequency. So here this part is chosen. Now if you see this imaginary part, fine. So imaginary part must be 0 because the characteristic impedance of this line is purely real. Fine. So you can again see for which value you are getting having better this imaginary part close to 0. So for this part, so you can do some trade-off, fine, to have this width. So that means by only changing or different widths, we are not able to have this equal to this real part and this equal to 0, right? So, and if you plot this omega beta diagram, you can say, so we'll see graph like this. So here this is your alpha part, and this dotted line is your beta part. So if you see this region, this part, so here your beta is 0. Beta is 0 means wave is now not propagating, and your alpha is suddenly very high. So this alpha very high is not representing the leaked power. This is representing, since beta is 0, so that means wave is not propagating. So we have a standing wave. So that is representing in terms of like if you have very high loss, so this loss is in terms of your wave propagation. So that means your wave is not propagating properly. Fine. So this is similar to like when we discuss the cutoff, before cutoff wave propagation. Fine. So now in this region we have open stop band. Fine. So we have to mitigate this. So we discuss this for different part. So alpha beta. Now if you put slots like this, so you have variation of imaginary part like this, real part like this, and if you put all these three, so you can have this mitigated open stop band. So this is the optimized, you can say, dispersion diagram of this unit cell. Fine. So here you can see this beta is not zero now. This is coming down and going suddenly up. So that is, this is phase change here. So if you see, and this line, dotted line, is basically, you can say, air line. Air line means dispersion diagram of air. So this line. So that means to have fast wave, your this beta line should be below this line, air line. Then you will have this Vp by C greater than 1. And this will happen if you take in original equation n equal to -1. So that's why this is written n equal to -1. This is also n equal to -1, but this is fast to be. Similarly, if you have here, so this will be n equal to -2 and so. Fine. So this, and this part is n equal to 0 part. Fundamental mode. So here some fields are plotted, current density, and so final structure is this, and this is the movement of your radiated beam with frequency. Fine. So you can see with frequency the beam is steering. So you can use this to scan a large area. So I am leaving this part because this is just measurement part, and so some other design based on this dielectric image line is this. So here perturbation is some A-shaped and some bend here. So this is able to generate a circularly polarized wave. Similarly, you can put this perturbation instead of your metal, you can put some other dielectric. That means you can load with other dielectric and you can have similar this. So here if you are putting some other dielectric, so some means challenges, so precise cutting of the gratings, positioning at precise position, and then we have to stick them. So you have to use some adhesive. So this will may not be perfect. So we proposed one solution. Instead of loading with some other dielectrics, just drill a hole. That means basically we are doing the same thing here, what other people have done. Here basically we are changing the dielectric in this region, because let's say this is 4, this is 3. So effective dielectric is a little bit different than the main line. Fine. So we have some perturbation. So we have perturb using these holes, and we have done the same similar analysis. This is, you can say, dispersion diagram and some other relations, and this is your final design, and this is fabricated. This is measure results. These are measure results. So we can have high gain. So gain is between 10 dBi to 16 dBi, and this is simulated, and so, and this is published in IEEE transaction. So this is again scanning with frequency. Some other design using my own published paper is this one. So this is from other group, but they have used the same concept, and they have made basically this array and used for different purpose, and some medical application. So this is some result. Again here, same concept is used. It's instead of only disturbing this, they have this hole plus metal strip, and then optimize this. Now let me discuss one this structure. So in SIW, so if you put, am I audible?
Yeah.
Okay. So for SIW, same concept is there. Just if you disturb, so how to disturb? Just to cut some slots, right? So some slots are there. So I have taken from this paper. This is not my own paper. So here you can see this dispersion diagram. So again here, if you see this green, blue line is your beta, and this dotted line is your alpha leakage constant. So here you can see this beta is 0. Fine. So that means in this region, this frequency range, wave is not propagating. That's why again your alpha is high. So basically this is open stop band. And this region, the authors have named this backward region of radiation n equal to -1. And this is forward region. This is n equal to minus. And they have given some, uh, you can say circuit analysis or equivalent circuit model. So to do the same thing, so they have modified this. So initially there was only this part of different size. So they are putting one more slot. So this part is in transverse direction. This is in longitudinal direction. And these two are making a unit cell. Fine. So using these techniques, this now, this is this dispersion diagram. So if you see this, so now your this beta is coming and just changing the phase here, right? So here this point is for broadside radiation. So in this way they have mitigated this uh, open stop band phenomena. So if you see or go through this paper and see the input impedance, so basically means you can say this is all about impedance matching. So you can use different what I can say impedance matching technique and match this unit cell impedance, or you can say blotch. You can calculate the blotch impedance, and that should be equal to the your unperturbed line. Fine. Then we'll not have this open stop band phenomena. Okay. Again here one slot. So one slot is not sufficient. So they are putting one more this one via. So if this is capacitive, so they are basically producing some inductive effect, and these two combined will nullify each other, and this will be matched. So that analysis is given here again. So if you have only this slot here, longitudinal slot, so this is the diagram, and you can see here there is a small open band, open stop band. Fine. And if you put both together, so this will be removed. Fine. So obviously you have not to cut randomly. You have to do some parametric analysis or whatever and optimize this location and size and so you can do this. So this is fabricated and so I think with this I am done. And if you are if you have any queries, so I can answer. We can discuss. Thank you.
Thank you, Dr. Prasad. Now the platform is open to queries. If you are having any query regarding the lecture, you can ask here. Dear participants, if you are having query, you can ask here or you can drop your message in the chat box. I think there is no query.
Okay.
So we can resume this session after 10 minutes. So be here. Thank you. Thank you, Dr. Prasad.
Okay. Thank you.